The work Explainable Automation by Philipp Wintersberger, Nicklas, Thomas Martlbauer, Stephan and Andreas Riener is a cooperation of Technische Hochschule Ingolstadt with Spiegel Institute Germany. We consider this study as a first step to apply principles from the field of explainable AI to feedback systems in automated vehicles. Trust issues are a relevant barrier for a successful introduction of AVs. Especially overtrust is critical and already led to multiple accidents. At the same time, many potential users do not trust computers to control the vehicle at all. To eliminate such issues, a process called trust calibration should adjust trust and behavior to the capabilities and limitations of a system. However, the mere awareness of system limitations is not enough to prevent accidents, especially as most drivers are no domain experts. In a 2018 study by Victor et al., neither such knowledge nor supervision reminders prevented nearly a third of study participants to crash with an obstacle. Successful trust calibration requires to infer the trustworthiness of a system in a given situation that is described by a magnitude of contextual factors, or in other words, drivers must understand how the system will react given an ongoing environmental situation. One method to foster trust and understanding is by raising system transparency, so to provide feedback about the system's behavior. There has been a lot of work in this area in the past, for example by Kuh, Kunze, Häuselschmidt and their colleagues, just to name a few. Also our group has done research in this area, and we focus on augmented reality visualizations which can be generated by vehicle sensor data. Here you can see world-fixed annotations of the environment in an unpredictable foggy scenario, and such visualizations were able to significantly raise study participants' trust and understanding. But a question is, how can such prototypes that may work well in experimental settings be implemented in real systems? AR visualizations must be automatically generated based on the decisions of the intelligent algorithms that control the vehicle. A research area dealing with the question of how to properly explain AI decisions is called Explainable Artificial Intelligence. Initially, this field focused on case-based explanations, meaning that there is sufficient time to analyze and interpret how a system came to a decision. However, automated driving is an online process happening in real time, which does not, or at least for the driver, not allowed to deeply analyze how decisions have been made. A potential method to provide explanations in such processes is called automated rationale generation. In this process, human users provide explanations for state-action pairs. In the example on the right, that is described in an IUI paper by Eshan et al., verbal statements have been collected to describe why an agent took a certain action in the computer game Frogger. Given a large number of explanations and situations can be collected, an algorithm can be trained that can then automatically generate explanations in new and unknown situations. Finally, these generated statements can be evaluated in another experiment with a different sample. We could repeat this process to provide explanations by automated driving systems using augmented reality. Instead of the Frogger environment, we use the driving environment, and instead of verbal explanations, we would ask human users to annotate the scene so that the behavior of the vehicle is comprehensible and trustworthy. Because of technical and administrative limitations, we could not collect so many explanations to train an algorithm. Instead, we stepped back and wanted to answer two research questions. First, we wanted to know which objects in the driving environment potential users want to become augmented and which underlying reasons for these annotations exist. Second, we wanted to know if the desired amount of feedback is related to study participants' trust. We conducted an interview study with 56 participants who had to watch and annotate 8 driving situations that were presented in form of videos from the ego perspective. We recorded videos with different urban characteristics, such as multi-lane roads or pedestrian areas, and aimed for ambiguous situations where it's not clear how they will continue. After about 10 seconds, the video stopped and participants was told, "Imagine you could receive feedback from the automation about any object present in the environment. Please select all objects or elements which should be included in feedback so that you feel safe, that you feel the vehicle is in control of the situation, and that you would be able to identify potential errors." Participants received a printout of the last video frame and a pen to make their annotations. Of course, we emphasized not to annotate anything if they would not feel it necessary. For each situation, participants also rated their trust in the vehicle and the riskiness of the situation with scale items from the STS-AD. Then the experimenter asked participants to justify the selection and to give each annotation a priority value on a 3-point Likert scale. This process was repeated for all 8 videos. Here you can see one of the videos. The blur was added just for this presentation. In this scenario, a pedestrian reorients again towards his vehicle, other pedestrians are moving on the street. I will now show you some insights from a subset of the scenarios. This is a heat map of the situation just seen in the video, built on the priority ratings from all participants. On average, 4.61 objects and a maximum of 12 objects were annotated. Most participants annotated the pedestrians. 89% highlighted the one in the front, 73% the group of pedestrians in the back. The reasons were the proximity to the automated vehicle, that their intentions are unclear, or that some of them are vulnerable. Also, parked vehicles were frequently included. Nearly half of participants selected the parked van as it narrows the road and as it may occlude dangers such as other pedestrians. Overall situations, participants of the experiment emphasized to augment vulnerable road users like pedestrians or cyclists. Here is another situation, scenario 5, a multi-lane road with high traffic volume. On average, 2.54 elements were annotated. Most important was the vehicle to the right that was selected by 79% of study participants because it might change the lane when there is only little time to react. 43% of participants included the lead vehicle in the selection as it could brake unexpectedly and that is important for the EV to maintain the correct headway. Some participants also included the road markings. In this situation, those were not considered as that important. However, this changed in other scenarios, especially when road markings were connected to the safety of vulnerable road users. In this example, including a pedestrian crossing, 4.3 objects were annotated on average. Again, a high share of participants included the pedestrians in their selection because of their movement or orientation. But here, 41% also annotated the road marking of the pedestrian crossing. They emphasized that the pedestrians could enter the scene any time, causing the EV to brake. But also in other scenarios, objects that are associated with vulnerable road user safety, such as bus stops or signs, were included. We collected all these statements and categorized them into recurring themes as summarized on this slide. The most important reason for annotations was potentially unpredictable behavior. This was followed by impact, meaning objects were annotated as they could influence the behavior of the ego vehicle, and object properties such as size, orientation, and spatial properties like positions and proximity. Objects were also annotated when participants felt that they did not obey the traffic rules, for example changing lanes without indication. Finally, bad visibility due to obstruction was another reason for annotating large objects such as parked trucks. Further, correlation analysis showed that the number of elements that people annotated significantly and negatively correlated with their subjective trust, meaning high-trusting users made fewer annotations than low-trusting users and vice versa. To conclude, we reveal the list of relevant properties such as predictability and proximity to be considered in the design of AR feedback systems. Also, our results indicate that the amount of feedback should be personalized and thereby consider users' trust levels. However, it is an open question if we should even allow personalized feedback, considering that other in-vehicle systems are standardized. Also, although we ask participants to annotate in a way that they would recognize potential errors, this study cannot contribute to the overtrust problem directly, and future experiments are necessary. Still, the study is an initial step for applying Xi principles for AV feedback. I hope we will be able to collect data for machine learning algorithms soon, and in case some of you are interested in cooperating in such big data collection, feel free to contact us. Thanks for watching.